Howdy, AP PreCal, it's Ms. Kosh. This is Unit 2, Multiple Choice, Video 2. I can still keep track because it's only the second one. And so, let's see. We are looking at an arithmetic sequence. We're continuing here. His first year as year 1, the number of students earning a qualifying score in year 3 was, okay, hang on just a second. The number of students earning a qualifying score in year 3 was 52. The number of students earning a qualifying score in year 6 was 61. Okay, so a sub 3 equals 52, a sub 6 is equal to 61. They tell us it's arithmetic. Which of the following gives the number of students earning a qualifying score in year t, where t is a whole number? Okay, so we're looking for a sub t. This is ultimately our goal. So a sub 6 is equal to a sub 3 plus 3 times the common difference. Okay, so 61 is equal to 52 plus 3d. Subtract that, I get 9, divide by 3, I get my d value is 3. Okay, so a sub t, my common difference is 3. So at a sub n, my a sub n is going to be equal to a sub 1 plus n minus 1 times d. Does that help me? Do I know a sub 1? Not yet. Okay. Is this the best way to do this problem? I don't know. If you find a better way, comment below. A sub 3 would be equal to a sub 1 plus 2d. So 52 would be equal to a sub 1 plus this is 6. So subtract that. I am at 46. Okay, so a sub n is equal to 46 plus n minus 1 times 3. So a sub n is equal to 43 plus 3n. So is this true if I make this t? I don't see why it wouldn't be. So 3t plus 43 looks good to me. Okay, a computer virus. Oh, this is calculator active. You know, this is exponential, and we're going to do some of these later. I don't know that I feel like finding, well, okay, here's calculator. Okay. The security company performs a simulation to predict the number of computers that might be affected. Geometric, which I figured. The first day is day 1 on day 6, so g of 6 is equal to 750. Day 10, g sub 10 is equal to 3,200. It's the nearest whole number. How many computers on day 14? Oh, so this is interesting. G sub 10 would be equal to g sub 6 times r to the 4th. Okay, so we can plug in g sub 6 right here and then solve from r to the 4th. But notice this, g sub 14 is equal to g sub 10 times r to the 4th also. So I don't actually, they didn't ask me what r is equal to, but we can just watch what I'm about to do. I can say this 3200 is equal to 750 times r to the 4th. That means 3200 divided by 750, let's make that a fraction. 64 over 15 is equal to r to the 4th. Now I could figure out what that is, but I don't know that I care. What I need to do to find g to the 14 is take g to the 10, which they told me, 3200, and multiply it by r to the 4th, which I just found right here, 64 over 15. Okay, so let's see. Is this the only way to work this problem? No. Will this work every time? No, but would I rather work smarter than harder? Yes. Okay, so let's figure out what that approximation is. Is that an answer choice? 13,653. Looks good. Okay, that was interesting. Oh, good. We already did that side. Okay, so end behavior. Definitely, you have to know how to write the end behavior. They'll tell you as it increases or decreases without bound. You have to write that in the FRQ. So let's see what it looks like when it shows up in multiple choice. Here's what I know about this one. This is an exponential decay. Okay, so what is it looking like? It's looking like something like this. It didn't have a shift up or down. And so what is it going to approach? It's going to approach the asymptote y equals 0. Okay, that asymptote will change if the whole graph shifts up and down, but that's the only way that that's going to change. I just need to know, is it decaying or is it growing? Since this is smaller than 1, it's going to decay. So what can we say? The limit as it goes to positive infinity did not come first. Okay, positive infinity, we're going to go to 0. So not to infinity, positive, not to negative infinity, not to infinity, we want to go to 0. So let's check this other one. When I go to negative infinity, it goes to positive infinity. That's correct. This one behaves in the only difference is now we're growing. Okay, this one we are growing. This one, okay, so this one's a little bit different. So this graph also would look something like that. So I don't really feel like doing this, but on this one, what happens is we've been reflected over the x-axis. So now, like, so check and see. If I plug in x equals 0, anything to the 0 power is 1, or here I'll write it this way, k of 0 would be equal to, anything to the 0 power is 1, so that's negative 3. K of 1 would be negative 3 times 5 is negative 15. Okay, so what this is doing is our exponential growth problem got reflected and it's doing something like this. Okay, keep in mind, this is an exponential decay. This is an exponential growth. This has no name. So don't tell me it's decay, or it's not an exponential decay problem. It's the reflection of an exponential growth which has no name. So what's it doing? As we go to positive infinity, it goes to negative infinity. As it goes to positive infinity, we go to negative infinity. So I think this would be the right answer. We still approach this asymptote of y equals 0 because we haven't shifted up or down to change that. And so A is the best choice here. Okay, similar idea on these. This one is now an exponential. It would have been an exponential growth, but then they put in a negative, so we reflected. Okay, so we would have been going down like this, but now we've been reflected, so we're going to go, we're not going to actually hit 0. We're going to go something like that. Okay, plug in 0, I get negative, so this would be the point 0, negative 5 if we care. And then it's going to get closer and closer to 0. It's going to get less negative. So once again, has no name. It's the reflection of an exponential decay, but we don't call that anything. We just graph the darn thing. I mean, whatever. Okay, so as we go to positive infinity, we're going to go to 0. We had 2 choices. It's not this, it's not this. So what was it doing on the other side? As x goes to negative infinity, we're looking at these two, it goes to negative infinity. Nice. I don't feel like doing the next ones. They're kind of the same idea. The exponential function is defined by this, where a and b are positive constants. The table gives us values. Which of the following statement is true? Okay, so what are we doing? Well, our initial amount, when I plug in 0, so a is equal to 36. And then what did I multiply by? 1/2. Okay. And then b was equal to 1/2. So there's my equation. I can answer the questions. It's an exponential decay. Yes, because a is greater than 0 and b is between 0 and 1. Yeah. Decay because a is greater than 0 and b is greater than 0. B was not greater than 0, and an exponential decay does not happen when it's greater than 0, or greater than 1. I apologize. Exponential growth, no, it wasn't growth. Those values are getting smaller. It's definitely A. Okay, the next one is almost identical. I'll do it and then move on. Our initial amount was positive. Our initial amount is actually going to be, this graph was, they didn't give us a 0 amount, but it's still positive because you can't multiply a negative by something and then get all positives from there on out. Notice these are 1, 2, 3, 4, 5. If it's going to be, if either of them, A or B, is well, okay, A is positive in all of these, so who cares? On these, notice we're multiplying by 3, so it's a growth because B is greater than 1. I'm going to skip the rest of those. Oh, okay. So F is always increasing in the graph. It's concave. Okay, so here, when we look at this one, what's happening? This is an exponential decay. It's looking something like that. So the graph is decreasing, but it's concave up. So decreasing, we don't want increasing, and it's always concave up. There you go. Okay, now the question is, what if they had asked about the average rate of change? Because it's concave up, the average rate of change is increasing. And basically what you think of with the average rate of change is it's increasing because it's getting less negative. So notice how steep and negative it is and it gets less. Okay, there we go. This one is an exponential growth, so it's always, it's increasing and it's concave up still. Okay, let's skip a few. Let's come down to, we'll do this last one. This would have been an exponential decay because this is less than 1, but then we reflected. So this is not the graph, this is the graph. The graph is increasing and it's concave down. The graph is increasing and it's always concave down. I already did that side. Oh, okay. Same idea. Okay, let's jump to some of these. I kind of talked about it a second ago. This is going to be an exponential decay like that. Oh, pretend I can avoid my asymptotes. It's decreasing but concave up. So it's decreasing concave up at an increasing rate. So it's decreasing at an increasing rate. Increasing rate tells me concave up. This is concave up. So that's going to be answer choice C. This really bothers one of my colleagues. I love her dearly, but anyway, we think she's wrong. Okay, so this one is, it would have been an exponential growth that would have looked like this, but now it's been reflected to look something like that. So it's not this one, it's that. And it is decreasing, and it's concave down, so it's decreasing at a decreasing rate. Okay, I'm going to move on from those. Okay, so this figure, what conclusions can we draw from this one? Here's a piece of x. The following conclusion is possible. It's logarithmic. No, that doesn't look logarithmic. It looks exponential because it's kind of that sort of situation. But the output values are proportional over equal length input value intervals. Exponential does mean that the output values are proportional. They have a common ratio. The output values have a common ratio. And that does seem, so we were at 1, 1, and then we were at 2, 2, and then we were at 3, 4. Okay, so those are powers of 2. So 4 divided by 2 is 2, 2 divided by 1 is 2, 1 divided by 1/2. 1 divided by, did you hear what I said? 1 divided by 1/2 is the same thing as 1 times 2, which is 2. So we have output values. Where did it go? Output values are proportional, so it's this one right here. This is about the same idea. We're going to move on from that. Oh, quadratic. That doesn't look quadratic. Okay, so what was happening here? I'm at 15 here. I'm at maybe 7 here, or 7.5. Is that half of it? I don't know. Maybe not quite half, but they seem to be decaying. The output values, I think it's exponential. I think it's the same exact idea. Proportional. Yeah, okay, fun. Let's see. We're about 13 minutes in. Come back and I'll do this next one in the next video. I hope you like, subscribe, comment. Let me know how I can help you and we'll keep going from there.